करना है ना,
इसे अभी इसको एक्सेप्ट करना है मीटिंग में।
What we record all this and we will give it to the participants later on. So it will be easy. They will again remind whatever they have studied.
क्वेश्चन also
मोबाइल को आया ना आपका, मोबाइल में होगा।
planet share.
Fine.
And is it again? Fine. Yeah, we will explain. Okay. Minimize करो. इसको minimize करो. Factor मारेंगे. So can I start now? Are you ready? Okay. So what we are telling that wave function phi is the major complicated for its finding a solution of coordinate equation. Okay. So now how to construct that psi? If you can have a good psi in the sense that since it is an eigenvalue problem, the psi is called eigenfunction, so it satisfies the properties of the eigenfunction. So now basically this is I was talking about that we can construct a trial function that is phi by linear combination of the some basis function. That chi is called actually in quantum chemistry linear basis function. Okay, so and with linear combination of the basis function, you will generate this trial function, this phi. Okay, and that phi, and then from that phi, you can generate a one strata determinant. That strata determinant should be anti-symmetric. That is, I was telling your wave function should satisfy some norm. So one of the norm is that it should be anti-symmetric. So anybody is any idea that what do you mean by anti-symmetric wave function? Simple way. Okay, so I will just tell that basically when you are keeping the electron in the different orbital, now I am having a row and I am having a column. If I exchange this row and column, then the sign of the determinant will change. Basically, this is to satisfy the Pauli exclusion principle. Okay, so that is called anti-symmetric product of the molecular orbital. So now what I did, I constructed my phi, and using that phi, I have constructed the Slater determinant. This n is nothing but the normalization constant. This is number of electron. Okay, and then after getting my Slater determinant, what I will do, as I am telling that within this phi, I have constructed my psi, and this is called Hartree-Fock trial function. Okay, and then if I solve it, as I was telling you, we will do the energy minimization. So I have used this sign del of E. So this signifies that you are minimizing the energy. How we are to do the minimizing the energy? By finding a wave function in that wave function, in which wave function you are getting the energy minimum. Okay. So I already have told that if you get a true wave function, you get a minimum energy, and if you get a minimum energy, that state must represent the true wave function. Okay. So now I will not go to the details here. We will just say that if you make this wave, so I have used this single operator. Okay, and then I have used this 2 electron operator. If you make it 0, you will get this Hartree only, and if you get from there, you will get only E of y. If you add on, that will get a Hartree only. Okay, so Hartree is very inaccurate. Okay, so until you take the correlation, you will not get accurate energy, and that has been given by the Fock with the Hartree concept. And then you see that I, J and Ij, this is called overlap integral, and this is called basically 1, 2, this is phi I, phi j, and phi j, phi I exchange integral. So basically, this is this leads to the Coulomb integral, and another is the exchange integral. Okay, so I'm not going to the details of this integration because we will not involve any mathematical operation here. Okay, because finally we will go to the hands-on session. Is it or not? So now I have got my Coulomb integral, then exchange integral, then one electron integral. Okay. So now one electron integral and two electron integral. One electron integral is basically two center integral. Two electron integral is basically four center integral. Four center integral. Phi I, phi j, phi I, phi j, phi I, phi j, and phi j, phi I. So four center integral, but two electron integral. Where is the first one where one electron is there is only either phi I or phi j, phi j. So that is called two center, one electron, two center. This is two electron, four center integral. Okay. So this computer will do. We are not going to do the integration. Okay. But Hartree did it, Hartree did it by hand. Okay. So his father was a very good, I think, mechanical engineer. So father was very strong in mathematics. So his father helped to solve this equation. Okay. So now we have got our final equation. We will do the energy minimization. That whatever the exchange Coulomb and one electron operator was there, that I have conceived here. This is called Fock matrix. Okay. This F. Okay. So in that now you know that those who are aware of the matrix, that anything you put in the finally matrix form, that the solution of the matrix in terms of determinants is very easy, because when something is an array, it is very easy to get the solution of that. When something is disarray, it is very difficult to get a solution. So matrix is like that only. Okay, when you are putting all the parameter in some array. Okay, so that finally here also you see you started with the complicated function h psi equal to h psi. It was looking very difficult, and we don't know what about h. We don't know what about psi. Finally, what we are going, we have come to a purely mathematical expression. There is no wave function is there, is it or not? No Hamiltonian is there. Some coefficient, some exponential function. Later we will see that is called Slater, maybe a Gaussian, or somebody who is going to work in solid state planar. Okay. So now you see that it's so simple. We should not be afraid of that. What wave function is doing. We'll just see that you construct a molecule that I think Raymond and Raghibul and I think maybe Priya also will join. Maybe Protusi also will join. I don't know. So they will teach you how to construct a molecule, either Gauss view. Okay. And then you draw a 3D coordinates, and from that you initial guess. Yes, I have told you linear combination of atomic orbital. Then you will generate a molecular orbital. Then you see that you will define a Fock matrix. Okay, and then you do the diagonalization. I told you the diagonalization of Fock matrix will give you the eigenvalue. Okay, and that eigenvalue is nothing but the energy of the system for the molecular system. What you are going to do. Okay, so now when you are doing the energy minimization, any energy minimization when you are going to do, so you have to vary something. Okay, and when you are going to vary something means you have to check always. Suppose I am starting from something that some value is there. Now when I am putting another value, I always compare what was my earlier value. Okay, if I see that my earlier value, when I am changing something, it is coming same, I will do again. I will not do it again because I have done this. This is the only final solution I have got. So I will stop there. So that is the things here. The logic is there. What I am varying and I am doing the energy. If what parameter I am varying and what I am looking for, you can look for energy. You can look for some coefficient. Okay, you can look for orbital. Whatever you are looking for, you see that what is the change, final change, or what is the your just before the final value. If there is no change, so that criteria you have to give. That is called convergence criteria. Convergence criteria. So that you can put your own. If you have a very accurate result, you give a tight convergence. If you know I am not interested in very accurate result, a moderate result is okay. So you give a very moderate convergence criteria. Okay. So now this way we can solve this. Now here I want to say just mention one thing, and this is very important. That is called Hartree-Fock-Ruthan equation. This is why this Ruthan equation is important. If I don't expand my phi in terms of basis function. What there are two ways Hartree-Fock can be solved. One is that you just take the hydrogen atom function and you solve it numerically. That is one way. That is initially Hartree problem was solved. So that is purely numerical. Okay. And then Rutan, this is not fair. My wave function I can construct in many ways. Why I should limit it only that because then I'm limited by the hydrogen function. I should not be limited by hydrogen function. I can generate my own function. So then Rutan give the idea. Yeah, instead of that, we should go for my own way of designing a function and which can satisfy the true wave function. Okay, so that is the importance of the Rutan equation. Okay, so we have got energy value. We are able to solve our Hartree-Fock equation. We are able to get energy value. Now we see whether we are happy or not. Okay. Now you see that what it is telling that 99% it gives the correct electron. So you will be happy. Suppose you are doing something, you are getting 99% of that. You will be happy or you will not be happy. Most of them will be happy, is it or not? But electronic system, they are not happy with that. Why? Because chemists is not happy. Physicists are very happy with this. They are very happy with that. Whatever the property they are calculating, they are not bothered about it, whether it is having 1% error or not. But that methodology, that the algorithm is what to find. So they are happy with that. But chemistry people will be never happy with anything. Actually. Okay, they will always make things complicated. And also your life complicated. Okay, so you see that now if 1% energy error is there, and you just see, suppose you are doing a for hydrogen atom calculation. Okay, so that total energy is, let us say, 75 HP. 1% of that is basically how much? 1969 kilojoule. This is a huge amount. How much energy it takes for breaking a bond? Any idea? If you want to break a bond, chemical bond, let's say a carbon-carbon or carbon-hydrogen bond, how much time? It will be around 100 kilocalorie. Is it or not? So it is more than that. So you will lose all the information, na? How the bond is breaking, or is it or not? So can you use Hartree-Fock for any bond breaking and bond making? You cannot do. Is it or not? Now the things become more worse if you go for a higher electronic system. Instead of oxygen, if you go to sulfur, you see the error has gone up tremendously. So what does it indicate? So overall, I get a qualitative idea about the energy of the system, but I cannot use it for chemical event. Chemical event means participation of the valence electron. A whole chemical reaction, those chemical engineers, those who are working for the process of chemicals. So their product will be controlled by valence electron. And Hartree-Fock is miserably well to capture that. Okay. Finally, I have shown you that one table. You see that if you are interested in the bond length, that is not that much error. Only 2.7%. Okay. But if you want to calculate frequency, those analytical chemistry guys are very eager to know. That is 11.8. But if you go to the dissociation, the chemistry or chemical engineering, suppose you want to design a catalyst. Okay, so catalyst means some bond breaking will be there. Is it or not? You will use some surface, and then your molecule, another molecule will come. They will sit at the surface. They will make a complex molecule. Okay, okay. So in that case, the error is coming 28.8%. So 30% error means a huge error. Is it or not? So your product nobody will buy. Okay. So now people, as you say, the people are not sitting idle. They always try to that whatever the Hartree-Fock has done. So whether we can make a remedy of that. So then people has come with a post Hartree-Fock method. So they will use the similar way of doing that calculation. But what are the Hartree? Another question is that what Hartree means? What Hartree means that it is not able to capture that. So Hartree basically means the electron correlation. What it means is basically means the electron correlation. What is that correlation? Hartree, though it has taken care of the anti-symmetry, though it has taken care of the Pauli exclusion principle, but this missed two very important things. What is the important thing? Suppose you are having an electron. You are having an electron. Okay. So now, what is the probability of finding the another electron to that electron? It will be very minimum. They already have used Pauli exclusion principle. So probability of finding the another electron to the on any particular electron is drastically reduced. So that Hartree-Fock has not taken care in his formalism. Another is that when two electrons will come together, they are having a repulsion. They are having a repulsive. So basically, there are two kind of correlation. One is the Hartree has not taken care of the full exchange contribution of the electron, two electrons when they are coming together. Another is the Hartree has not taken care of the electron repulsion when they are coming together. So basically, there is a dynamic correlation. It means one electron is sitting, he is telling, "Hey, don't come, I am already there." Okay, so that is called dynamical correlation. That was missed in the Hartree. So then after that, to capture those exchange and correlation, that is called exchange correlation. I will come to later. That many theories have come into the picture. I am not going to the details. Okay, so basically that is energy, correlation energy. Okay, that correlation energy. Suppose you are having an exact calculation. If you can subtract 34, so you will get. You can tell that that is the my correlation, and that correlation has come to the electronic correlation. Okay, so for that there are many methods are there. This is one is the configuration interaction. In that, how they have taken care of that? That we are just thinking that electron, two electron is there, so there is two orbital is there, so they are sitting, but it is not there. That means we are confining electron in that. But electron may jump other orbitals. So there is plenty of virtual orbital. So the people have started taking of presence of those orbitals, and they have constructed the wave function further, and that they are getting the good result. So they are able to capture the correlation. So we are not going to discuss details on that. That is one is the another is the molar placid perturbation theory, and then another is the coupled cluster theory. I am not going to talk about details of this. So now I will come to that. Especially major people those who are using that is density functional theory. Is it not? We are all I think mostly going to work on density functional theory. Is it not? Those who are to do quantum calculation or any domain. Without DFT, you cannot do even dynamics also. Okay. So now I will come that how we can go ahead with this. So I already have told this guy is very simple. One electron, no issue. When there is one person, there is no problem to deal. Once you put another in your lab also, you see that the one person is there, he's happy. The side is paying full attention to me. No, if another guy is coming, then there is a rival. Side is paying more attention to that. So always two particle system always complicated. Is it or not? So here also same thing. Here also there is a two particle system, two electrons. So two electron, how to solve it? So basically now the Hamiltonian we already see. This is a T kinetic energy. This is the nuclear electron interaction. That is also one electron interaction. Keep in mind. Okay, we have approximated that. And then this U. This is basically this repulsion energy. So now how we'll go ahead with that? Fine. So now we are discussing our psi. So we cannot conceive what is psi. Is it or not? Huh? Psi is one tissue kind of thing. Is it or not? So important, but we cannot conceive what is psi. But we can understand what is psi square. Is it or not? Psi square nothing but the power density. So now I know the power density. So if I square root of that, can I get unit? So psi is nothing but the unit of that power density. If you take the square root of that, I can think that way. Is it or not? So basically, now people's idea is that let us forget about psi. Can we come out with something else, which also can equally play the role of psi? Okay, so people have started trying to find out. I want to find a guy who can replace psi. Okay, so people are working on that. So now, what is that physical observable I can think, I can use instead of psi? The work is going on. Not only that, that quantity I want to find, it should satisfy all thing, all that A psi or E psi kind of what I say boundary condition. Is it or not? So okay, people have started working. Okay, so he was, Schrodinger. Let us take an example of Benzene. How many electrons are there? 42 electrons are there. Is it or not? So 42 electrons means each electron having a 3 coordinates. Is it or not? X, Y, Z. So how many? 126 coordinates. So I can construct a wave function for benzene by taking the 126 coordinates. I can forget about spin right now, but I can add also. Therefore, 42 electrons are there. So there will be up and down. So 42 spins are also there. So total that many coordinates I am having. Okay. So now see, if you go follow the wave function formalism, suppose you are in a hydrogen atom, 1 electron. How many coordinates? 3. So with 3 dimensions. If you have a helium, how many electrons? 2. So you have a 6 dimension. Then you go lithium. How many electrons? 3. For the dimension? 9. So let us jump to the carbon. So 6 electrons. So your coordinates, how many? 18. So if you go away, you see that the dimensionality of the system is going and increasing. But can we calculate that dimension? Higher dimension can we calculate? We cannot calculate. That is why we have taken the one particular approximation. Is it or not? So no computer still now in future also can do this high dimension calculation. Maybe quantum computer can do that. Okay. Now question is that these two guys. This is his guide. This is Hohenberg, Pierre Hohenberg, and this is Walter Kohn. They come up with the idea that let us take only density. The density only having a 3 coordinate x, y, and z. No business with psi. Okay, fine. So life is quite good. So they are developed in 1964. Okay. So Schrodinger, he developed his wave function theory in 1995. He got the Nobel Prize in 1933. And this guy, that Walter Kohn, along with his guide, Pierre Hohenberg, he developed first the theory, but he could not give the application. He could not give sufficient data that really his theory is working. Okay. So then the Poppel, George Poppel, basically who is the developer of what? Many people use Gaussian. Huh? Who is the developer of Gaussian? John Poppel, you know? Huh? So that John Poppel, basically he's done extensively application of that DFT, extensively. Because he has not developed the DFT, but he extensively applied the DFT and a lot of things. So he finally came up with a company. You know, Gaussian is a company, you know? Gaussian is it or not? So who are using Gaussian here? You know the Gaussian is a company. Okay? So therefore, from a chemistry, you can open a company also. I just Professor Banerjee can tell how is the turnover of the Gaussian worldwide. Is it or not? There are so many company has been opened due to DFT or the other I can say computational chemistry. You have heard media has, you have maybe heard Schrodinger. Is it a cosmology? So there are so many computers. SCM is there, Synopsys is there. And the turnover you see that from the company is huge that. When you can go to that pharmaceuticals. Pharmaceuticals nowadays is mainly run by computational chemistry. All the pharmaceuticals, even your that during Corona, what is the structure of Corona? Who gave the first structure? You know, it is given by the computational chemistry. You know, first structure of the Corona has been given by the computer. After that, medicine was developed. You know, so it is a huge implication that DFT. So once it is proven by John Poppel, then the Nobel Committee was satisfied and they gave him in 1998 the Nobel Prize jointly with Kohn and Poppel. Okay. Now, so as I was telling that you just give how density is fine, it will can give everything. You just make a comment and you will go ahead. It is not like that. You have to prove that it is working equivalent with the function. So they are trying to correlate. If I have told you that energy how I am getting, this expression already I know. Is it or not? The very simple principle. Already I have told that H is nothing but the expectation value for which the true wave function. I am starting with the trial wave function. I will reach a true wave function only if the energy is minimized for that psi. Okay. So this is already we have got. Same thing should be happen for density also. So already in case of density, if you see that if you convert that whole Hamiltonian, I will come later. I will show you that I can convert whole Hamiltonian instead of wave function. I can convert into the rho density. Okay, in electron density rather. So in that case, this is the nucleus interaction with the electron. So this is the electron density under which it is having interaction, and the integration of what volume, whole volume, and plus another that whatever thing is left, or otherwise whatever thing is not taken here, all are taken care by this one functional. You see how intelligently they are taking the concept. I know which is well defined. There is no ambiguity. I am keeping that function. But what that is the ambiguity is there. I can define some function, and I am calling that the universal function. If I know the universal functional, if I can define universal functional, my problem is solved. Okay, so there is no issue. I can get energy exactly what he is giving if I have a true wave function. Okay, so now funda is that how to find this guy, universal functional. Okay, so then if I get a universal function, automatically I will get my true density also. And if I get my true density, I will list my true energy means true energy here means ground state energy. Okay, so I have to find out the now ground state energy. Okay, if I can able to find out the correct ground state energy, I will get the correct function for that also. And then automatically I will get everything, all the molecular property I can calculate using only density. Okay, so when this debate is going on, then this Dirac, okay, fine, this essay is very good, but everybody tells that how to solve it is very complicated. People just don't understand, don't conceive what is this psi, what is this anyway. So very difficult. So then this, I told you this. Now, find that you know the functional skill I know. So we are blind. Yeah, we don't know. That guy has told when man they have told that you definitely you are having a density, and that for that density definitely you will get a minimum energy. But still we don't know what that density. And if I have to get that density, how I will get it? That they are not telling about that. They are happy that this is a thing. But that is true. It is there. But how to get that? Nobody is telling. So this is like a blind man. So this guy is a blind. So he does not. He has never seen an elephant. Okay, he has listened the story. So if somebody is telling that this is elephant, I have seen the elephant. Okay, if he can catch the trunk and he can the whole body, as if he is thinking that he has, but by taking part of that body, he is thinking that it is elephant. Okay, so similarly the problem of the functional also. Somebody, if you see that those who have already done DFT, they will know that a lot of functionals are there. Is it or not? Lot of functional, I think it is there. You don't know which functional is working for what. Okay, but everybody is telling that I am doing great job. Is it or not? So now, slowly I want to see that how the density can replace a function. Replace in the sense it is not a true sense of a function, how it can work instead of psi. Okay, so for that it has to satisfy like this. It has to be a function of some position. Is it or not? It has to be correlated with some atomic number. Then total number of electron, it should be correlated with the total number of electron. Then so finally we said that let us say density means let us electron density can work for that. Because if I do the integration of the electron density with the probability density, I can get the total number of electron. Okay. So this is the thing. If you see that probability density or electron density can be defined like this, and if you do the integration of this density in the space volume, you will get a total number of electrons. So overall, the electron density now it is satisfied. It can give the total number of electrons. So we are a little bit moving towards a picture that is captured by wave function also. Okay. So now that position and now this another interesting point is that if you see that when you are solving the Hattie-Fock, you will see that if you plot the orbital, you will get always the density peak above the nucleus. Okay, so that also it is able to capture by this electron density. So then means electron density can capture that phenomena also. Bond breaking, where the bond is formed, where the bond is not there, bonding, anti-bonding. So that property also you can capture by electron density. Whatever the wave function was able to capture, electron density also can capture that property. Okay, and also in the maximum also in the cast. Cast means if your function is like this, that is called split cast. So that also it can capture. So far, electron density is being good thing. Still, we have not constructed the function now. We are still the electron density may work. Why? Because it is satisfying these things. Okay, so then finally, so now we can find out the atomic number of the element. How? Because if you take the derivative of the average density related to position, you will get this relation. I'm not going to derive that. So from that, JD is nothing but the atomic number. Our R is already told that average density. So we are able to calculate the atomic number also of an element. Okay, from the density, if you know the average density of the system. So we are much closer to the periodic periodic table, because if your things what you are going to construct or design, finally your objective is that it should satisfy the whatever the element in the periodic table is there, all those elements properties, is it or not? So now what I have told you, the given density one could form the Hamiltonian operator. I will come to the next slide. That all in a full Hamiltonian, what we have constructed in terms of psi. Now you can replace the psi in terms of density. Yeah. Now you see, this is my nucleus electron attraction. Okay. So earlier I was using phi there. Now no phi is there. I have replaced it with the density. Okay. Now the repulsion term there I have used phi. That you can see that phi I, phi j, phi j, phi I, as well as phi I, phi j, phi j. Is it or not? So those terms vanish now. I have written in terms of density. But I will see that later whether this is correct or not, because this is a classical expression, and this is also classical, but this is correct. But this expression is correct or not, we will see later on. Okay, because this is totally classical. It is what it is telling basically that you have a multi-electron system. You have taken one electron. You are telling that electron is interacting with another electron. That is another position. So now we don't know because it is electron and indistinguishable. So you cannot define that way, na? So that means you may be counting twice same electron. Okay, so that is why half is there. Okay. So now I have replaced nuclear electron attraction by density. I have replaced electron-neutral repulsion by density.
The I is small.
So
orbitals are in different shape and size. So in previous slide, it's like stably every is taken this.
It is the approximation. Okay. Still, we are not here. That all we are going through an approximation. Finally, all approximation what we have done, we will put in the functional, universal functional, because it is a thing. Wherever I am taking something approximation, I have a opportunity to take that as a in that function. That is the beauty of this lattice function. Wherever some deviation is there, you put it. That is why you are getting so many functional. Is it or not? If anion is there, you use this functional. If cation is there, you use this functional. If neutral molecule is there, if hydrogen bonding is there, if molecule is very large, you use this functional. Why? Same functional. So those what you are taking, those deviation is taken care by some extra parameter. Okay. So now we have got nuclear electron in terms of density. We have got electron-electron repulsion in terms of density, and now the kinetic energy. This is given by Thomas Fermi. I'm not going to details all that. So this is kinetic energy I am getting in terms of density. In nuclear electron attraction I am getting density. I am getting repulsion. So all three measures I am getting in terms of density. So I have now constructed my Hamiltonian. Okay. So now that I was talking about that this I have used. Suppose you forget about this. You have taken this. I have shown you that I have told you that it is not correct. Okay. So now I will say the why it was not correct. You just see. If you not forget about this part, as if it is not there. You just take this part. Suppose if you having a one electron, only one electron. So this term is a basically two electron system. It should be 0. It should be left side should be 0. Is it or not? So left side should be 0 means you forget about that. It is not there. So this thing is 0 or no? It is not 0. Is it or not? Because basically it is giving self interaction. As if same electron is interacting with the same electron. So something is wrong in this definition. Is it or not? So that is why this expression is added. This is called whole function. So now if you want to cancel it, when one electron is there, it should satisfy the limiting condition. So to satisfy the limiting condition, people came up with the idea to add a whole function here. So basically, what is that telling? If electron is positioned at R1, you keep a function around that R1 and it varying over R2. Okay, so that if this guy is giving a positive contribution, this guy who gives exactly negative contribution to make it satisfy this limiting condition for one atom. Okay, so why I am telling this whole function? Because finally it will be related to the exchange and correlation. That is the bread and butter of what whole density function. If exchange functional could have been 0, the DFT, so many papers we are still publishing. We could not have published any paper. Isn't it not? Because we are able to publish the paper only due to that exchange functional is not universal. If it would have been universal, we could not have published, and now it is no paper. So that people could have finished their job early. So we could have to thought about something else. Okay. So now the same thing I have written here. And whatever I have told, it is written there. So why the exchange functional has been done. So then that already I have discussed about self interaction. So I'm not going to repeat it here. Then it is also not required here. So I will go. Yeah, fine. So now just it is not required now because already I have told the whole history that Hohenberg and Korn they gave a 2 theorem. One theorem was that there should be a one unique potential. There should be a unique potential. Or that unique potential there should be a one unique density. Or either I can say like this: for a particular single density, a particular density, you cannot have a 2 potential. Okay, so that is I am not going to prove it. Just I want to share it. So because that has helped a lot to define the functional. Okay, that is one thing. And another thing is that now where we were, we have given the potential energy all 3 in terms of density. So that means all energy functional E of rho we have got in terms of density. If you add these guys, this one, and this one, so they are the total energy. So E of rho, is it or not? And then you see that only I have written here. This is okay, and this you see that was the Hartree-Fock term, repulsion term. Okay, Coulomb integral in Hartree-Fock. Okay, this already we can write. Already I have shown it that how we can write the attraction part. This part we don't bother about right now because it is just a constant term. Nucleus repulsion. It is not bothering electron. So you can just separately calculate. You can once your final computation is done, you can add that. Okay, so basically we are bothered about this thing. So now we have got kinetic energy, this guy. Now we have to find out this guy. Okay. Now this is also very simple to write. We will use the Fermi model here, kinetic energy calculation. So now we have to calculate this. So the major task is how to calculate this. Okay, so now come to the rescue in the so far Hohenberg and Kohn they have developed the theory, but now how to put in the practical, that idea was given by Sam. Okay, another I can say Kohn and Sam. So basically now you have got a functional, and that is a kinetic energy, and that is a now I was telling why we are using this Hartree, because this term is nothing but the exactly Hartree term. Because in Hartree term also we have finally replaced that repulsion term in terms of density. So now we have to find out this guy. So now if we are able to find out this guy, then our job is done. But who is stopping us? This exchange coordination. That exchange coordination already I have told how that exchange coordination is coming. One is that when you are putting an electron, it will not allow the other electron to come. So that is the one thing, that the exchange. Okay, and another is that the dynamical correlation. The electron will repulse all other relation. So that is from these 2 terms basically come to the exchange correlation. Okay. So now I will go to the final. So here also that the electron density you can calculate. They already have shown that from the power unit density. So now you can calculate from the square of the orbital actually. Okay. But you have to consider this phi is occupied by each phi is occupied by the 2 electron by means of Pauli exclusion principle. So now I can convert that whole thing in terms of H psi equal to E psi. Okay. So people call it as a case constant operator. In case of Hartree, I have shown you that Fock operator that you can remember that. Okay. That F. Okay, phi F phi equal to E phi. Similarly, this is now is represented by HK. It is called quantum operator. So if you can solve it now, now life is a bit easy. So now still is not easy. So what is the exchange potential? So that you have to define. For that also people have find a solution. This is that if I having energy, okay, or exchange potential energy, I can take a derivative with respect to density. I will get the potential. Okay, root is there. So now again that how to get that. So now we'll come to the. I'm not talking about the comparison already. I've told you. So now we'll come to the. So what is the similarity between Hatifa and what is the difference? We'll go by part. So it will give a very good understanding. So both follow Madison principle. Why I'm telling you this? That I have to satisfy that density what we are going to use density. It is not violating any norm of the wave function theory. It is going as parallel with the wave function theory. Okay, so then you see that as I told you, the Fogg matrix and the quantum matrix, they are almost similar. Okay, so both are using this inter-electron repulsion using the classical. So we are at par with the wave function theory. Is it or not? So now here also quantum equation, since we are able to recast in the Hartree-Fock, so we can do the matrix formulation also. Is it or not? So we can do the diagonalization also. So now we are at par with the Hartree-Fock. But what extra advantage we have got? We are able to add that exchange correlation. So chemistry is happy because now we can do the bond breaking and bond making thing of calculation. Is it or not? So basically, you see, Hartree was a self-constitution procedure. This is also a procedure. Okay. So basically, now what people usually do, what you are doing the calculation right now, basically you are doing the DFT calculation on the Hartree code. Because Hartree code, whatever the function orbital it is generating, one electron orbital, that you are using as a starting point for your DFT calculation. Because you have to give a gas density there. So gas density, what we are using from the Hartree orbital. So the likeness has become very simple. So we are not putting extra code that. Already existing code, whatever the function theory is there, you just use that theory and you add the density functional part. So your life has become very easy. Okay. So it is a difference between Hartree and KS. Already I have told you. So basically, only the difference is that only you are coding in that in terms of 3 coordinate system, and the function is on the n-dimensional system. That is the only difference. So you have reduced drastically a multi-dimensional problem into a 3-dimensional problem. That is the beauty of density functional theory. So all sort of things already I have told. I'm not going to tell you details. Now the question that how to find that guy. So now it is up to you what you want to use. So what is your system? You have a periodic table. How many elements are there at the present? I know it is 112 or something more than that. Anybody has any idea? What is the present periodic table contents? 100. 180. 118. So now you have to try to find out what you want from the 180 element. And you are trying to find out what the existing functional is there, whether it is working for your system or not. If you are not happy with the existing functional, there are a lot of functional. You develop your own functional and you come out with a new functional and it will be given in your name. Okay. I would say that how people are getting name from just developing a functional. You see, so now one is that local density approximation. What is the meaning of local density approximation? It is a constant density. It is a constant density. Some of you are having a nucleus and you have an electron. So as if that electron density is continuous throughout from the nucleus to up to the orbital. But is it true? It is not true. Is it or not? Those there will be a gradient of electron density. Now from the nucleus, whatever the density will be there, it will not be the same in the outer. No? So you should have gradient density. So then people come with a GGA function. Okay, generalized gradient approximation. They come with the instead of rho r, they add a del of r. Okay, then people have come with a mega GGA. Okay, so they because in case of kinetic energy, you have taken a Thomas Fermi expression. Then some error is there. So now I can calculate directly kinetic energy also. So they have given one extra task for kinetic energy. So those are called meta GGA. Then some people have come, Hartree was quite good. Hartree was quite good. So the extent part he has taken Pauli distribution principle very correctly. So if you vary that and if you attach with DFT, you will get a very good result. So some people have come with a hybrid. So that is called hybrid. Okay. So local, GGA, meta, hybrid, and now it is going on. You see, people have started from the Earth. They are trying to go to the heaven, means chemical accuracy. So they have started with the LDA. GGA, meta GGA, hybrid meta GGA. Now, you can work on the direction whether we can get a fully non-local function. So if you can develop, you can open a company like Gaussian, and you can, if people are publishing a huge number of paper, in future you may also can get into a price for that, for the universal functional. Is it or not? Because once it is a fully non-local means it will be universal. And if it is universal, it should work for independent of any element. Okay. So now the LDA functional people have used by different Thomas Fermi, then Slater, then Wegener. I'm not going to talk about details. Then as I was talking about the different popular functional, maybe those who are working now right now with DFT, mostly people use the B3 I think. Okay, anybody is using B3? Some people should say yes. Huh? No, you using B3. Is it or not? Why you are using B3? So it's worked very nice. Demand is basically using numerical. Right? So that is a figurative. Okay, fine. Okay, so now there are different kind of. I just have given what I got from the literature, but you can, for your own problem, you can take the help of this, or you can search more literature, and according your system is there. Whether it is a hydrogen bonding system, or it is a pentadol bonding system, or whether it is a tension element. Because for each element, whether it is a D block element or it is a F block element, so property varies because valence electron act differently. If your core electron is that's why the F element is there. So there is some relativistic effect in there. So you have to take a relativistic effect. Correct? So depending upon your choice, depending upon your application, you have to choose your function. Okay, there is scope is there. Okay, once you can go on publishing until there is a some person kind of universal function. One is people publish a universal functional, your job is in danger. So you're not able to publish many over now. So you have to find out another theory. Wave function, density function, some other theory you can develop. Okay. So I am not going to details problems with DFT. Now I will just give you now slowly I will give some example. Okay. So up to DFT, first part is there. Is it or not? Huh? Up to DFT. Na? So I will give some example. You see that just I have taken from some literature. This is the density functional theory, BLIP 630. You see, this is the guy. This is the molecular size, it is going increasing. Okay. Here the GPU time. Okay, your calculation time. You see the size of the molecule is getting increased, but DFT GPU time is not much increased. Is it or not? So, what is the meaning of it? Any idea? You are increasing size of the molecule, but your GPU time is not getting increased. But increasing very slowly. Linear scaling, have you heard about it? Huh? So, linear scaling. So, DFT is a very good linear scaling. You can very scale very good with the computation. If your size is increasing on the molecular side, it will not take much time. But in other cases, it will be exponential. You just see this guy. Your system was C2H6, it is comparable with the DFT. Then from there, you have got to C3H8. It is okay, fine, still bearable. Now, if you go there, you just this guy, what has happened to MP4? Exponential. So that means it is not linear scaling. Is it not? Just you have gone from this C3H8 to C4H10, not much change in the total number of atoms. Okay, so that way you can see that DFT is the best linear scale. So if you are able to find out a good functional, then you can get all the molecular properties, whatever the molecules you are interested. Okay. So now I think many people know what is this codes, is it or not? So mostly people are using Gaussian here. GAMES USA also maybe free software, some people may be using. Okay, then this I think this is but it is all a paid software. I think Demol, I think you are using it is a commercial software. You're probably so your body. What is the cost? You know, no, your boss knows. So okay, so Baki, this is free software. Orca, anybody is using? Yeah. Anybody has heard the name of Orca? Orca, no? You have heard. You are not using. So what you are using? Version here is okay. So this is the popular QM code. After that, what is there? This is the reference book. I follow this book as very sincerely. This is density functional theory of atomic molecule. And it's a very wonderful book. Those who want to go deep in density functional theory, they should read it. Very fundamental book is there. And other, I think, some people maybe have read this book. Quantum chemistry, Ira and Levi. Whatever the lecture I have given, I have followed Ira. Okay, so I follow this book. Very, for students, that is very good book. Ira and Levi for understanding. And this is also good, I think, this guy, Kramer. Kramer also you can read because Kramer, what he has done, he has tried to link that book to the application. Basically, molecular property, and that book is basically linked to the chemical engineering property. Kramer. So that is good for the chemical engineering. Okay. And Jensen book is very nice, though it is voluminous, it is a very nice book. And then Leach also is quite good, and this has become this Grant and Richard. So you can go through this. This is the references book. Then I don't know what is the next. So I will get a bit give which is what is I was talking about. But there I have not told what is the type of Chi I should use there. Is it or not? So Chi, how we can select, very important how to select the card. So you have hard definitely slatter orbitals. Is it or not? You have hard Gaussian. Is it or not? So mostly those who are using Gaussian, they are using Gaussian type orbital. Means this orbital form is like this. Okay, or slatter, the orbital form is like this. So what is the advantage of Gaussian is that if you do the integral of this, you will get the same function back. So it is very easy for you to do the integration. But in case of this, you will not get the same function back. So this is difficult to integrate. But the advantage of slatter is that it actually close to the actual orbital or to the experimental observed. Whereas Gaussian is not that. So, but if you take a more and more number of Gaussian, you can represent the slatter. That is why if you see that when you are doing a Gaussian calculation, you take a lot of 6, 3, 1, plus, a lot of things you take. So I think already those who are using Gaussian, you know why you are using. Is it or not? Who is using Gaussian here? Is it or not? So you are using 6, 3, 1, 1. You understand what is the meaning of 6, and then what is the meaning of 3, and then what is the meaning of what is the meaning of those? So finally, if you add on those things, it should represent a good slatter orbital. That was the objective. Okay. So like this. So slatter orbital is like this, and Gaussian orbital is like this. So if you go on adding, finally this guy will represent this guy. That is a funda. Okay, now the people actually don't read this kind of thing. Why I'm adding more and more Gaussian. So basically, it is to finally to capture the slatter property. Okay, and now this is just I have given you that different kind of orbital function, how it is being defined, different kind of orbitals and how their shape is like. Okay. So that what Priya has told that only I have told here. So what is the meaning of this 6? What is the meaning of 3? What is the meaning of 1? What is it or not? So now that is the thing. So now you have to add some polarization when you are adding polarization. That I was telling. When you are dealing a particular problem, you will know better than any other what you should choose for your function. Yeah. Okay. So if literature is available, you can take. Otherwise, you can just give some diffuse function or some add function. For the if you're having anion or excited states, we used to add diffuse function there on that. Okay. So you don't have to add by hand. Computer will do it for you. Is that right? Okay, so then you have heard of the Polish consistent basis set, because I have told that if you are able to generate a waveform set which goes to the true waveform, but to adding to goes for a true waveform set is not a very easy job. No? So if it was a very big basis set means automatically you are adding more number of functions. So adding more and more number of functions means adding more and more number of integrals. Is it or not? So you have to do that all the integrals. Is it or not? So those integrals will take time. So then you have to see that whether really it is worth of doing the large number of calculations, what are the molecular property you are trying to calculate. So if you are going to calculate a bond length, and if you are going for a very large basis, it is of no use because bond length does not depend strongly on that. But if you are going to some electronic properties, okay, so dipole moment, polarizability, those may depend on those things. This was an energy. Those can depend on those things. So you have to think before using them and say, no, somebody has reported this very big mix report. Immediately I should report it like that. You should think what property you are going to calculate and accordingly you should choose your decision. So now then pseudopotential. Pseudopotential, I will come tell you details about those who are interested in periodic DFT. Periodic DFT, what is periodic DFT? That also I will discuss tomorrow. So, but in case of this thing also I was talking about that now your heavy element is there, isn't it not? So 4 electron, whatever is there, its velocity will be very high, is it or not? Due to the nuclear, because the number of proton is huge, is it or not? So it will try to drag it, I will not go there. So you start, is it or not? Is it or not? So that will, velocity will go and increasing on the 4 electrons. So that means it will reach to the fraction of the velocity of light. The fraction of velocity of light, you have to take care of the relativistic error. So those things you have to take care. So those things can be taken care by the pseudopotential. Okay, so fine. Then this I will not going to explain now. Already I've told it. Then what is there? This is also another. So no, sorry. This I will take after lunch. I will details. So now I'm stopping here. If anybody has any question, I am happy to respond to your question, to your queries, any kind of. Well, if you don't ask question, I will. The ball is in your court. And I can ask for some board also. So, no question. So good. Huh? Question should be there, isn't it? Any question. It's not that what I have taught that only. If of your own interest also question. Pseudopotential, effective potential, basically both are same. There is no. It is a terminology used by different people. They are same. You want to ask something?
Regarding my project, like
You can discuss anything. It is not because the subject.
I'm working on CO2 sequestration in other side. It's like a type of crystallization process. So in this, the bottom molecule actually surround the guest gas molecule. So can we use DFT that?
So your problem basically is that you want to capture CO2.
Yeah.
And that CO2 should be captured by some molecule. Isn't it? So what is that molecule?
It's like water case.
Only water case. So it is a hydrate type. Just people are working on methane hydrate.
Yeah. Same.
So similarly with the CO2 hydrate. Even to say that. Density function theory means just what is your objective property?
CO2 and
now what is your objective property? What property you are looking for so that you can use it? What? So that should be further defined.
Okay.
What do you want to do that? Is it interaction?
Yeah.
That CO2 water interaction or the solubility of CO2 in water? Something you come up that I want to. This is my index parameter. Okay. So let us. I can say that. Let us say the CO2. You are interested in CO2 solubility. You are interested in?
So actually, the hydrate formation only occurs after the.
Now you are only, if you are interested in only structure.
Yeah.
If you are only structure, then you can use the periodic version of DFT. Though system is not periodic, but you can use that AM basically. I will talk more that you can use. Otherwise, you can do forceful based, but the forceful you have to generate of your own. But though CO2 force field and water force field are well developed, but during the system when it is forming hydrate is working or not. So that is I told if you are able to define a property index, then you can choose which molecular protocol is signature protocol is you will use. So if it is solubility, you can go for even Monte Carlo will be best for solubility for well, you can use like a Gantt and Monte Carlo, and you can solubility calculation is very good. Or just if you want to go for isolated structure, just do the same thing. So that will give only the isolated parameter. Yeah.
Is there any difference between the density calculation of solid state or molecules?
Yeah. Then again, it's coming the forward. So molecules and so any whatever so far I have discussed, if you see that just now I show you that orbital flutter and that what I say Gaussian. What is the form of that? It will be minus alpha, it will be minus alpha square. And if you see that form, they are located on what? They are located on the center of the atom. So basically, those are the atom centered system. Those are on the atom centered system. They are not fluidic in nature. But when you are going to solid, any solid, so that all they are in an array in a fluidic. So they will work, but not as efficiently as a fluidic. Your computation cost will go up there, and the result of what you will get is maybe the correct one. So in that case, you can use. That is why I will be talking about the fluidic reactivity. Fluidic reactivity means how in that case we don't use in general this guy Flutter and Gaussian. We will use their planoid. And what is the advantage of planar tomorrow? That I will take. Then in case of solid, you should go for a planar based. That I will. Yes, Patricia. It is basically already dispersion correction is there in it. Already it is. So for some basically it work for transition metal, but the transition metal will interact with some large system. So for that it works. But the user of the QC is very less. If you see that, you would just for the sake of comparing some data, use that. Otherwise, there is no wide user for it. And I myself also sometimes publish some news just to give some variety in the one. Only using B3 sometimes I get bored. So let us add some Anglo6 to me into the column, but it is not giving extra chemistry or extra nothing. Yes, Dr. Regular said. So if you want the answer right now, I can tell, but since the geometry optimization is coming after lunch break, so I will answer it, but it will come after lunch break. So your question is that whether we are interested in Hessian or whether we are interested in figures.
Yeah, because sequential we have constant calculation, but geometry optimization is not required. So then what is the role of most part?
In geometry optimization, we don't do the Hessian calculation.
Question basically, they don't require the input as a calculation of post constant. But when we are doing the frequency calculation, we have to with the post calculation.
It is not like that. When you are doing the frequency calculation, that time it is printing. Because when you are doing the geometry optimization, definitely you are doing the second derivative. If you don't do the second derivative, you will not come to know that whether you have reached the stationary point or not. What is the stationary point? That point you have reached the minimum energy. Yeah. Now the stationary point may be saddle point also. Is it not? So you have to change that. Whether you have a really saddle point or is the equilibrium. So for that you have to change the second derivative. Okay. So basically, during geometry optimization, always we do the second derivative also. But in case Gaussian, it does that. Not only Gaussian, even I am using extension Tarbone and ADF. They also don't print that until you give a comment. So that is it. Otherwise, always is there. Because that is the only criteria you can certify that you have reached equilibrium limit. Otherwise, you cannot certify that you have reached equilibrium.
That is the question basically. They don't require the input as a calculation of post constant. But when we are doing the frequency calculation, we have to with the post calculation.
Yes, You want to say something? Okay. That is also in the second half. So, what I can tell that there is the second half is there. Huh? Okay.
After that, we have hands-on session.
Huh? Oh, the same man. Yes, yes, yes. Oh, I was just getting conscious. Oh, after lunch. No, I will not. I don't want to start critical after lunch. Just now. I was thinking some confusion was there that I have given only one lecture and second half part is there. Oh, I will just finish first. No. Lunch, after lunch, I will not do that. Okay, fine. So it's good. In the way we have charged basically. We have become charged now by doing some extent. It's good. So people those who are sleeping now, they are come out from the sleep. Is it so nice? One day I was just watching on a video, a lecture by a professor, very famous professor in MIT. He's a electrochemistry basically. He's a electrochemistry. He was talking about band theory. He's a electrochemistry, but he was talking about band theory. And that how from the molecule, suppose you are having a lithium atom, you are adding another lithium atom, you go and adding lithium atom, is it or not? So then if you draw the HOMO and LUMO of that lithium atom, so finally all the HOMO and LUMO will be closed step. Then from you will see that discrete energy relative will get a band, is it or not? So that is why the band concept is coming into the solid state and HOMO LUMO is basically what takes people. Finish then they go band. Okay. And they can and also they use this valence band conduction band. Or chemistry people with higher HOMO and they are confined to that. So always there is segregation of the subject. Okay. So I was watching the lecture. So in the that guy and then the first row on guide you are sleeping. Okay. So I just what I say that lecture is a very good, very famous lecture. I'm not getting his name. He does not bother about the person is sleeping or not. In our case, what happened? If somebody is sleeping, I have lecture in the day. Hey, what you are doing here? You are sleeping here. So that lecture I saw that just not. So once that came up, so then the lecturer asked, "Can I help something? You are not. You are disturbed by something." What he wants to say that maybe he has got some disturbance in the night, is it or not? For that he may has not got good sleep. He is sleeping here, so maybe he needs some help. So it is not that he is, come here, you are not putting attention to that. Indian people used to do that. So this is the beauty of the. So like, people always, whenever somebody is sleeping, it is not due to that. It's not some issue maybe with that. So you need to help that guy. Is it or not? Okay. Yes. Apart from that, so you know that equilibrium. What is the equilibrium means? Suppose I want to say what is my equilibrium. If I want to define, so I have to have some position. Is it or not? Not even position. Some plane should be there. Is it not? If I go to the hill. If I keep one leg here, if I put in the valley here, and then say, what is my equilibrium? Can I say what is my equilibrium position? Is it or not? So I should have some space. I should have some plane. Is there some landscape? Is it or not? So in the landscape, why I'm talking about the landscape? Because landscape will lead to the potential surface. Is it or not? So I come to the potential surface next. So now the equilibrium geometry means that you are having a geometry, and that geometry means it is a collection of some atoms. Is it or not? It is a molecule. Then once if there are atoms are there, that means they are position is fixed by some coordinates, is it or not? And once it is you know the coordinates of the atom, so that means you can represent a geometry or molecule in terms of some mathematical function, is it or not? So if you know a mathematical function, and you can always say that mathematical function is a minimum or not. There is a lot of energy minimization algorithm is there, and you can calculate, and you can say that your For a mathematical function, you are telling that your molecule is in equilibrium or not. So beautiful, is it or not? So one-to-one mapping is also good mapping between the mathematics and the geometry, is it or not? Okay, so already I've spoken this thing. Now the potential energy surface. So potential energy surface, what do you mean by potential energy surface? Potential energy means it is a function of position only. There is no contribution of the kinetic energy. Is it or not? Am I correct or not? Potential energy should be only function of. But by the kinetic energy, suppose I am a molecule. I am a molecule. Let us say CH3OH is there. OH is getting broken. I am getting H minus or H plus. It has become CH2O minus H plus. So what will happen to my potential energy surface? So some potential energy I will lose or not. Right? So that potential energy, what will happen? It will convert to kinetic energy. Is it or not? Is it correct or not? No. If your CH3OH was there, if I abstain H plus from that, so you will get a CH2O minus. Okay, so that molecule is a bit unstable or not?
Yes.
And that whatever the H plus you are getting, that will go as a kinetic energy to the system. But overall, what will happen to the energy of the system? It will be constant. That is the constant. No? So if that is not satisfied, that means we are doing nothing. Is it not? Okay. So that means what is that? Why I am telling you that what is the importance of potential surface? The potential surface is very important when you are doing a calculation. Is it or not? So how we construct a potential surface? How we construct? So for constructing a potential surface, we have a minimum 2 and more than 2. So if it is a more than 2, our potential surface will be very complicated. It will not be 2-dimensional. Potential surface engineering we used to say into dimensional, but if it is more than 4, it will be multi-dimensional. Is it or not? So that is very complicated. So here what I have told that another thing is that let us sorry. Okay, here I was there. Suppose you are having a molecule which have -6 number of degrees of freedom. So n is nothing but the response to the atom. Okay, in case of water, if it is 3n means n is the 3. Okay, 3n minus 6, and then 3n minus 6 how many? 3 minus 6 how many? Minus 3. So minus 3 minus 3. Three only. 3n minus 6. N is what? N is 3. What N is you are considering degree of freedom of what? Nucleus or electron? Let us say forget about that. What is the degree of freedom for water molecule? 3. Somebody has told 3, no? It is correct. But how you have arrived at 9? Huh? So how? Using that relation, you have to come out.
The 3.
So that is so that is somebody has to be 6 minus 6. So 3 degrees of freedom. Is it or not? Okay. So no confusion, no? Okay, it's very simple thing. Okay. So now what I say that if you want to draw a potential surface, you have to have a minimum 2 coordinate. Okay, minimum 2 coordinates. Is it or not? Suppose I am here. Okay, so I cannot just define my position by only one position. Is it or not? Minimum 2 position I have to do. Then only I can draw a potential surface. Okay, so how that I have drawn a potential surface, I will show that. That is a water molecule. Okay, so how we can say the potential surface we have? You see, this is the landscape, your landscape, where I am standing here. Okay, this is your energy. Okay, and this is your, you know the water molecule. So you can take one bond length as a Q1, 1 degree of freedom. I will take the HOH bond angle on another degree of freedom. Okay, so now if it is fixed, okay, so in that optimized condition Q1, Q2, whatever the energy this guy water molecule is having, that is the minimum energy. And this, when if you do the construction of that surface using this guy Q1 and in this Q2, you will get a surface like this. So this is known as a potential surface. Okay, so that is the funda potential surface. Any question on the potential surface? I can discuss right now. Okay, if it is not there, I will go ahead with that. So now, as I was telling, the molecular geometry is nothing but function. Okay, suppose if water is there, so you know that you can represent water in terms of either Cartesian coordinates or in terms of internal coordinates. So what is Cartesian coordinates? You know, it is exactly. What is the internal coordinates? Exactly. Bond length, angle, diagonal angle, those are called internal coordinates. So both we can use for as a, when you are those who are doing the hands-on session after lunch, they will tell you that whether you are using input as a Cartesian coordinate or input as a what I say internal coordinates as a molecular input. Okay, fine. So basically, always it is better always have to have a Cartesian coordinates. Right. For small system, internal coordinates may be quite good, but for large system, you can you don't know that what kind of angle will be there, what kind of angle will be there. So you can avoid that killing. Sometimes your job is killed if you have a molecular size is big. You know how big a molecule you have used so far in the optimization. Anybody? For big means what is the total number of atoms size? How many? How big you have used? You have used. 10 to the 6 atom. Try. Yeah, try. What is the molecule of that? What is the molecule?
Because I tried to make a multi-element surface. I tried just to put a computational load on a system.
Now, what is the system? What is the system?
Sir, it was a cluster, newly formed cluster in our lab.
Now, what is a molecular system?
Molecular system was just a simple graphic surface for interaction, embedding with the zinc particles.
So what is the total number of atoms there?
So the order was 10 to the power 6.
10 to the 6 atoms.
We formulated the design. I used Burite to just formulate the design. I tried to implement it. It didn't work out because that time I didn't have an idea about the computation.
Okay. So then he's telling his experience that is actually correct. So basically, when you are going for a large system, so it is always better to go for a Cartesian coordinate. Because for large system, if you go for internal coordinates, what is the input parameter you are getting? That is mostly erroneous input actually. So if you give run a big system with a erroneous input, after certain time you will see that the job has got killed. And if you try go again and again, you will never succeed. But if you go with a Cartesian coordinate, and because Cartesian coordinates, you will close to the system, but it may not. You are not giving a wrong input in the system. So that is why, from my experience, always go with the Cartesian coordinates for the optimization. Okay. So now, as I was telling that, what I was discussing about molecule. So molecule, I can represent in terms of position, is it or not? So I am having suppose water, I can represent in terms of position, 2 or 8 hydrogen. I can go instead of water, ethanol. I can go for a glucose. I can go for a bigger molecule, bigger molecule. I can go for a corona itself, is it or not? But is it or not? I think corona is having that's something I think about that. Okay. So the more bigger the atom is, that is better to go as molecular system is there, it is better to go for a Cartesian coordinate. So now, what actually a geometry optimization done is basically you are constructing a mathematical function by taking the positional aspect of individual atoms. Okay, and then after getting the mathematical function, you are just magnetizing that function that at which position of different position of the atom with respect to the electrons, it is relaxed or it is seated. Okay, and then from that you are getting that your minimum energy, and from that after once you have got your minimum energy, you are calculating all the structural parameters. You get some type of moment you needed some other element actually consider if you want. If you want to calculate spectra, you can calculate add spectra. So a lot of things you can calculate. So basically, the definition of then is geometry optimization is nothing but the energy minimization. Okay. So now that I was already have answered that about the regular was taking that when stationary point, and the stationary point I should check whether it is a geometry optimized structure or a saddle. So if it is a saddle point, then you have to have a double derivative. Double derivative is called basically Hessian calculation, because from there we used to get the force constant. And if you know the force constant, using this mu equal to 1 by 2 pi root over k by mu, we can calculate the frequency. So we can calculate the IR spectra of all the systems. Okay. And then, so if it is a single negative frequency, we will call it saddle point. If you have a two frequency, then we got a second order saddle point. Okay, one first order saddle point, second order. And if it is a positive, your double derivative is positive, we call that I have reached my equilibrium geometry. Okay, that is the things I have written here. Okay, so now same thing I have written that in terms of matrix form, basically Hessian, whatever is there, as I have told you that if you can array all information, suppose you are calculating this derivative, first derivative, second derivative, so you can array all those in the matrix form. So if you do the matrix form, always your calculation will be faster, because since he is telling that I want to go for 20%. So that kind of calculation, if you don't do a matrix, you will not get. Never you reach to the result. So always that is all finally whatever the calculation you are doing, finally you are going to do the mathematical function or the mathematical function. If it comes into the matrix form, it will be that will be easy. Okay, because calculation will be easy. Okay, so now how we do the energy minimization? Basically, we do the energy minimization either by a Newton reduction method or by the quasi-Newton. Have you heard of the Newton reduction method? Have you? Good. Quasi-Newton. Achha. Those who are doing Gaussian, I think they that follow what? Any idea? Anywhere in the Gaussian manual, have you read in time? It is written anything that whether it is a Newton reduction or it is a quasi-Newton reduction or it is a conjugate gradient or it is a sequence distance. And Gaussian it is together. Okay, fine. Now, basically, I will not tell you that. So now that already I've told you how these things actually happen. Whatever you are calling geometry. If you put in terms of block structure or schematic, this looks like this. Is it or not? So you get the initial geometry that today they will show you. And so that is Dogi was asking that the Hessian. Sometimes people store the Hessian in the from the previous calculation, and that they are using an initiation of the second calculation. Okay. Then you calculate energy and gradient, check for convergence. The convergence is what is the convergence? I just now was talking about the gradient and displacement. You can check the displacement also that after moving the position, that whether the displacement is causing any change in the structure or not, or you can change the del of E by dr. If it is 0, so that means you have reached your equilibrium geometry. Okay, so if it is done, fine. So your work is done. If it is not done, you just repeat it. Okay, these things I have written because it is in the software. They are using this because they are making your life much easier. So if you just do the Newton reduction or quasi-Newton, it will give you a result, but not that first. So some people are adding onto that some computational efficiency. So that is why they are leaving added onto that. Okay, so now Patricia is talking about this transition state. I think this is this. You can see that how we can calculate the transition state structure. Because suppose you want to say that this is my structure, whether it is transition state or not, I want to calculate. So you just do the geometry optimization, and then I get a ruler state. Derivative calculation, Hessian calculation, and just check it whether you have one whether the frequency or not. If it is there, then you can say that. This guy is a or this complex. So that is the matter. Okay. So you are not going to do anything. Everything will be done by computer. So don't worry. Right? Okay. So but you have to know the terminology. And yeah, I want this for this. But if you know the basic idea of this, then you'll be much more helpful to interpret the result so that you can submit to article journal, and so that they are happy, then they have done a good job. Huh? Okay. So now this anybody has the idea about this how detailed lesson is done? You know na? Is it not? Very simple, na? Is it not? Huh? But this is only implemented in the algorithm. Okay. So those who don't know, for them I was just telling that basically you just want to find the root of the equation. Okay. So how do? You just take a guess on that. Let us consider this x1 is the root of that function f, and this is I can rewrite it as x0 plus lambda. And then you and for that root, if it is the root of this fx, it should be 0 for that particular value. And then you Taylor do the Taylor expansion of this function f of x0 plus lambda. So you will get f of x0 plus lambda into first derivative of that function. Okay, so that should be 0. So then lambda is nothing but the my movement of that position. And if you, I can rewrite it this guy. If I put this value here, so that my equation will be x1, x0. So now if I go on repeating of this, so basically xn plus 1, x1, this I can repeat. The same thing can be represented by the graphical representation here. Okay, so if you do this one at x0, the value of fx0 is this value. You take a tangent here, and the tangent will cut here. So then x1 corresponding to the you find out the value of x1, fx1. You have again you take a tangent, then you will come down here, and again if you put this value to this function, it will cut the function here. So again you take a tangent, this way you will go, and this way you will go to the minimizer. So finally your objective will be the effect should be 0. So where the effect will be 0 at which value of x, that is your objective. So this is the way of energy minimization is done. So you see, you have started from the each side or each side. Finally, where you are landing, no one function, no Hamilton is there. Is it or no? Huh? So why to afraid about that function and why to afraid about that phi? Is it or no? Finally, you are doing a mathematical yeah. So there is other method are there as you are telling. This is the steepest descent method and the conjugate gradient method. Steepest descent method basically they are biased direction is there. You have a gradient. So the gradient you can put in the positive direction, you can then the negative direction. So if you go on negative direction, if you know the function, so your function is like this. Okay, so you this curvature like this. So if you this is your f of it, and this is your that I have shown here. So you can take a position little bit here, take a point here, line search, and you will cut another the function here. You take that value, and then again merge this element. This way you will cut, and finally you will get a value. So if you want to see, I can show you that here. I'm talking about in one dimension. Okay, suppose you have a function like this. Okay, so initially you are here. Okay, so now you are given a small displacement, so you will be here. So in that displacement, if you do a line search, you will cut this function here. Okay, so then you will do a more displacement here, so you will cut a line here. So this way, if you can go, if you go this way, this way, this way, finally you will reach it. This point. So this will be your equilibrium limit. That is the followed by steepest descent. So basically all the same in the technique. Only the people are using how to make it fast. Okay. So now then conjugate gradient, what this guy it is to make life more easier. This guy saves the gradient. It always saves the gradient for the next calculation. So that your geometry is actually very fast. Okay. So then this is done for geometry optimization, and now I will be a little bit happy. I used to use carbon wool, but I think they will show Gaussian. So but I will never use them. Never use Gaussian, but I think Lemon has used Gaussian. So you can, as somebody was doing how to. Somebody was asking me how to draw a molecule. Is it or not? So one Tmolex software is there. It is free software. You can use Tmolex. Other molecules are there. So I have generated a molecule. So this is the gradient. You can see that how it is coming. It is energy versus cycle. Cycle is nothing but the function of R. So initially it is very sharp. After that, the gradient is 0. So that means you have reached your structure. And this is called homology. I think you already know how to construct the homology. What is the significance of it? Okay. And then as I was talking about how to choose a functional, so I have just taken an example of water molecule. You could see that B3 lift GBP, SBP, and BP. Almost identical value. If you see that there is on the structure, functional does not have much effect. Okay. Then it is a water dimer. In case of water dimer, also I have shown you that different how the one water molecule is attached to the another molecule. And you are talking about that. So instead of water, you take a CO2 molecule and just check how the thing is. For initial stating. After that, you can choose what is. But finally, you have to define what you want actually. Until you want, know what I want in terms of some average value. So then it will be easier. Okay. So then the different functional. Then Raymond did this use a Gaussian. Just I wanted to check how Gaussian using this functional. This functional is not available Turbomore, but it is very good for taking care of the. You can always remember anybody has used this functional. It is very good for dispersion correction. Okay, so this functional, this is a bonding. You can see 1.917. This guy is giving 1.908 or 909 something. B3 SDP. Or as B3 TGTP, it is giving 1.937. You see there is a difference between this guy. Whereas it is 1.9. So BP is giving quite good result. So a single functional cannot give everything. You see, BP is better than B3 if you consider this is the best one. Okay, so those people used to say that B3 is the best functional so far. But why? Because it is average. In average, it works for all the systems. That is what. Then I did. I haven't. How much time? 5 minutes. Okay, na? 5 minutes. Okay, so then because why I'm showing you the benzene because it is a very rigid structure planar. Okay, so it does not have much effect if you use what functional you are going to use it. It doesn't matter basically much here. Okay, well change is not much. Okay, this is a benzene for different functional. This I have made specially for you people because this is useful for class actually, isn't it? But it is not going to give you any publication or something. Okay, until you add all kind of functional. So there are 100 functional if you add, and then you can come out a conclusion is that this is the best functional. You have to come with a mean average error kind of thing analysis. And you have to do some statistical analysis. If you add some statistical analysis with a non-functional, then it may fetch some new application. Okay. So then if you water and benzene, so your name I have forgotten. Huh? Jagendra. So as you are talking about instead of CO2, I have to have benzene only. So you can put that. Just I wanted to see how benzene work with water. Okay. Because I wanted to show you that how benzene work with benzene. So that is why I use benzene and water. And so now this is benzene, how benzene work with benzene. So if you use B3 TGTP, people used to say it is a very good functional. Okay. So it cannot capture the dimorphism benzene. It cannot predict dimorphism benzene. You see that bond distance, what it is saying, it is 18.998. Is it enough? So people are happy. Oh, you have not, suppose you have not seen the structure. You have just done the energy calculation and you are calculating the interaction energy. So you are thinking I am done a great job. But basically, if you see the structure, your structure is not an experimental predictor structure. Is it not? So, but then I asked Raymond something is wrong here. So Raymond did the Gaussian. Okay, he was same function and it is coming a very good structure. Then again, I repeat the Raymond structure here using the not again B3 leaf, but very high resistance. And now see that it is coming very good structure. They are not parallel because it cannot be parallel. The electron repulsion is there, so it will be sliding. If you see that those who are aware of the graphite, the graphite slide basically. This kind of basically this is due to this phenomenon. Okay, so if you want to do the geometry optimization of a molecule, molecular system, cluster, so you have to be very careful what functional you are going to choose, what basis set you are going to choose. Okay. So I'm not going to tell you those who have used the Gaussian. I think it is given the Gaussian. I think na it is given the Gaussian na. So it is there. I'm not going to talk. Read it out. Finally, after all presentation, it will be shared to you. Okay, all whole presentation will be given to you. And then I'm not going to share to you. So this is the references here. Thermochemistry, shall I go still now after lunch? Thermochemistry part is there. And then firstly, they can do the hand-on session. Okay, in the thermochemistry. It is in the hands-on session also it is there. Thermochemistry. So it will be good. But basically how you can do the thermochemistry calculation, that part is there. with some results are there, then I will, no, I will not take part that part. And then I will tell you after lunch, this is important, basically, not this part, population analysis. You are interested in population analysis? You do population analysis? Anybody does population analysis? You have heard about population analysis? Gaussian people should do that. Okay, so about that also I will tell. I will not take much time. I think that how to calculate the chart in the atom and how to calculate bond order, whether it is double bond or single bond, that kind of things will be useful for the interdimensional structure. So right now I am closing here, and so after that lunch we will start with these two, then parallel exercise. Okay, well these two will be mostly linked with the Hansen system, very intermittently. Okay? So I can stop here. Okay, thank you. And any question is the Hansen system, a lot of people will be there, so we can understand from each other. Okay.
So we break for lunch. We meet again at what time? 2 o'clock? Fine. At 2 o'clock, we meet again here. Okay, lunch is served at the first floor of the college.
Just make PDF.
I'm not reporting to this.